Welcome back to my channel. Let's continue solving problems from the 27th Philippine Math Olympiad qualifying stage. We are now on part 2, problems 11 to 15. Problem 11. Let A be a complex number satisfying the equation 2a squared equals 5a minus 4. What is the value of a raised to 3 over a raised to 6 plus 8? Alright, this type of problem has become a standard item in many mathematical Olympiads, especially at the qualifying stages. And the usual approach to solve this type of problem is just to manipulate the given equation or expression so that we can see some connections between them. So let us do that. Let's take first the given expression a raised to 3 over a raised to 6 plus 8. What I'm going to do first is multiply the numerator by 1 over a raised to 3 and then multiply also the denominator by the same expression 1 over a raised to 3. By distributing this, we have 1 over a raised to 3 plus 8 over a raised to 3. And notice that we can write 8 over a raised to 3 into the cube of 2 over a. Now, to simplify the denominator further, I'm going to let b be equal to 2 over a. So, the right hand side becomes 1 over a cubed plus b cubed. Now, let's set this aside first. Let's take the equation 2a squared equals 5a minus 4. Notice that if we divide both sides by 2a, we get the equation a equals 5 over 2 minus 2 over a. And take note, we also have 2 over a in the right hand side. So if we rearrange this, putting 2 over a or negative 2 over a in the left hand side, we get a plus 2 over a equals 5 over 2. And take note, earlier we let b be equal to 2 over a. So let us do that also here to get the equation a plus b equals 5 over 2. Alright, so now we see some connections. Take note that here we can actually factor a cubed plus b cubed because this is just the sum of cubes, right? So this denominator becomes a plus b times a squared minus ab plus b squared. So now we can just substitute here the value of a plus b, but before doing that we can also manipulate this factor so that it will contain the expression a plus b. Now take note that negative ab can be written as 2ab minus 3ab. Now we can factor a squared plus 2ab plus b squared, and then we get this expression. However, we have an extra variable here, a times b, right? So how do we get the value of a times b? Take note that earlier we have that b is equal to 2 over a, right? So if we cross multiply, we get exactly ab, which is equal to 2. So now we can just substitute the value of a plus b and ab. So the final answer here, the value of a cubed over a raised to 6 plus 8 is 8 over 5, and that is option B. Problem 13. Let S be a set of positive integers, each of which is at most 2025, such that the product of any two distinct elements is not a multiple of 27. What is the largest possible number of elements of S? Alright, so how can we generate set S with the largest possible number of elements? We can start with the set of first 2025 positive integers. Of course, this set does not satisfy yet the given conditions in the problem, since it is possible to pick two distinct elements from this set whose product is a multiple of 27. In particular, the product of these two distinct elements is a multiple of 27 when one element is a multiple of 3 and the other element is a multiple of 9. Now, it's clear that if we remove all elements which are multiples of 9, then it's not anymore possible to pick two distinct elements from the resulting set such that the product of the two elements is a multiple of 27. Although some of the remaining elements are multiples of 3 but not of 9. Alright, so let's count the multiples of 9 and then subtract that number from 2025 to get the largest number of elements of set S. So how many multiples of 9 are there? We can just compute the floor of 2025 over 9 and then we get 225. So there are 225 elements to be eliminated from the original set to generate S with the largest number of elements. So let us subtract 225 from 2025 and we are left with the maximum number of elements of S. So the answer is option C. Problem 14. In triangle ABC with circumcenter O, let D be on side BC such that AD bisects angle BAC. If angle BAC is obtuse, quadrilateral ADOC is cyclic, and angle ABC measures 54 degrees, what is the measure of angle ACB? Here's the diagram. Let us start by connecting points A and O. Now notice that central angle AOC and inscribed angle ABC intercept the same minor arc AC. Hence, the measure of angle AOC is twice the measure of angle ABC. So angle AOC must be equal to 108 degrees. Now, since quadrilateral ADOC is cyclic, and by the properties of cyclic quadrilaterals, we know that angle ADC is equal to angle AOC. So angle ADC must be equal to 108 degrees as well. Now, focus on triangle ABD. We know that angle ADC is an exterior angle of triangle ABD. And so by the exterior angle theorem, we know that the sum of angle ABD and angle BAD is equal to angle ADC. Now, plugging in known values or measures, we have 54 degrees plus angle BAD equals 108 degrees. So angle BAD measures 54 degrees. Since AD is a bisector of angle BAC, we know that angle CAD, this one, also measures 54 degrees. So now we know that the measure of angle BAC is 108 degrees. Now we can easily get the measure of angle ACB. We can just subtract angle ABC and angle BAC from 180 degrees. So we have 180 degrees minus the measure of ABC, which is 54 degrees, minus the measure of angle BAC, which is 108 degrees, 54 plus 54. So we get the result 18 degrees. So that's option D. Problem 15. Given that log of 5 to the base 2 is approximately 2.321, how many positive integers k less than or equal to 100 are there such that there are exactly 4 powers of 2 with exactly k digits? Note that 1 equals 2 raised to 0 is considered a power of 2. Let us break down first what the problem is really asking us to do. The problem is asking us to find groups of exactly 4 powers of 2 with the same number of digits. For example, you can easily see that there are exactly 4 powers of 2 with exactly 1 digit. These are 1, 2, 4, 8. Here, k is equal to 1. Also, there are exactly 4 powers of 2 with exactly 4 digits. These are 1024, 2048, 4096, and 8192. Here, k is equal to 4. Let us describe the values of k here as valid. Now, the problem is really asking us to count the groups with such property, which is the same as counting the valid values of k. Now, since k is less than or equal to 100, we're just going to look at those powers of 2 with at most 100 digits. And I'm going to use this approximation to count those powers of 2. Alright, so with this given, we have that 5 is approximately 2 raised to 2.321. Multiplying both sides by 2, we have that 10 is approximately 2 raised to 3.321. Now I'm going to raise both sides to 100. So we have that 10 raised to 100 is approximately 2 raised to 332.1. So what can we get from this? Take note that 2 raised to 332 is less than 2 raised to 332.1. And since 2 raised to 332.1 is approximately 10 raised to 100, we have that 2 raised to 332 must be less than 10 raised to 100. So this further implies that the powers of 2 that are less than 10 raised to 100 with at most 100 digits are 2 raised to 0, 2 raised to 1, 2 raised to 2 up to 2 raised to 332. And obviously there are 333 powers of 2 less than 10 raised to 100 with at most 100 digits. Now, I'm going to divide the 333 powers of 2 into groups by dividing the interval from 1 to 10 raised to 100 into subintervals using consecutive powers of 10 as endpoints. So if we do this, we must get 100 subintervals. Now let's look at the powers of 2 in each interval. For the first interval, obviously there are exactly 4 powers of 2 with exactly 1 digit. So k here is equal to 1. For the second interval, there are exactly 3 powers of 2 with exactly 2 digits. For the third one, also there are 3 powers of 2 with exactly 3 digits. For the fourth one, there are exactly 4 powers of 2 with exactly 4 digits. Alright? So now we've found two valid values of k, which are 1 and 4. So what's the key observation here? Obviously, an interval contains either 3 or 4 powers of 2. And we are really interested in counting those intervals that contain 4 powers of 2, right? Now another way to see that there are either 3 or 4 powers of 2 in each interval, we can consider this inequality where x and k are positive integers. Now, if we get the logarithm to the base 2 of each component of this inequality, and then applying some logarithmic properties, we get that k minus 1 is less than or equal to x times log of 2 to the base 10, less than k. Dividing both sides by log of 2 to the base 10, we get that x is greater than or equal to k minus 1 over the log of 2 to the base 10, less than k over log of 2 to the base 10. Now let us determine the interval length by subtracting the left endpoint from the right endpoint. By doing that, we get 1 over log of 2 to the base 10. Now let's get the approximate value of this. We can apply the change of base formula to the denominator to get log of 10 to the base 2. And take note that we can break this down into log of 2 to the base 2 plus log of 5 to the base 2. The first term is just equal to 1, and we have the approximate value for log of 5 to the base 2, which is 2.321. So approximately the interval length for x is 3.321. So what does this mean? This means that there are 3 or 4 positive integer values of x that fall on this interval, which further implies that there are 3 or 4 powers of 2 that fall between two consecutive powers of 10. Okay? Okay, so now what I'm going to do is I'm going to let m be the number of intervals containing 3 powers of 2, and similarly I'm going to let n be the number of intervals containing 4 powers of 2. And since there are 100 intervals, it must be that m plus n equals 100. And since there are 333 powers, it must be that 3m plus 4n equals 333. And as mentioned before, we are interested in counting the intervals containing 4 powers of 2. So we are interested in finding the value of n. So by elimination or by substitution method, n must be equal to 33. And so the answer is option B.